All right, let's go ahead and get started. Kind of where we left off on Wednesday, and I think the important takeaway is not necessarily the exact memory layout for our structures, and they are kind of essentially placed component by component adjacent to each other in memory. But the more important takeaway I think from this slide was once you have defined your structure, your rest of your program and the language treat your struct variables as any other variable type. And the implications for that are something that maybe you'll only really get to see once you experience it, but it can make what would otherwise be kind of messy coding tasks a lot more straightforward when you have structured data. Just for example, you can copy entire struct variables from one to another without having to worry about manually copying every element. I have student one, I have student two, I can set student two equal to student one, and it will copy all the components of student one into student two. Essentially, it's a large memory block transfer that you get without having to worry about things like string copy or mem copy or other those types of functions. You can also then have your structures as variables for function inputs or as a function output and return an entire variable of that structured type, right? We talk about the limitation of our functions otherwise, that if I want this function to update three things, well, there's either pointers or globals or other kind of workarounds, but this approach is a pretty natural thing. If the three variables you want to return all relate to each other, you wrap them in a structure, then you just return one variable of that structure type. Finally, as we'll see in a couple of the examples we'll be working on today, we can have we have arrays inside our structures already, like first name and last name in our student type. But because C in our program will treat a variable of that new structure type like any other variable, you can also then have arrays of your structures. And then combined together, that allows for, with just a few characters, a few lines of code, to be able to define quite a bit of memory and be able to do quite a bit with that large amount of memory here. So where we left off was this somewhat intentionally complicated example is, okay, we have students, that's one structure. We can then have an array of students inside a wrapper structure we called class. We can have an array of classes inside a wrapper structure we called department. We could wrap multiple departments inside a university. We could go on and on as much as we want. But the rules are at least logical and consistent for how we access those individual elements. You essentially do the array syntax first, that's square brackets to figure out, of my array of structures, which one do I actually want? The ith one or the third one, or whatever that offset may be. And then once you have the structure within that array of structures, the single structure within that array of structures, then you just use the dot operator to determine, okay, I have the 27th student in this class. I want to know their name. I then do dot first name or dot last name once I have the individual structure. So array syntax first, then the component operator, which leads us to the example that we had left off on Wednesday. And I commented out because it wasn't going to compile because we hadn't defined all those types. But we had the third offset, not exactly the third letter, of the first name of the 12th student of the 4th class in the 5th department. And it's kind of debatable whether, in terms of wrapping your head around this kind of synthetic example, is it easier to work from left to right or from right to left? I guess it's just depends on how your mind works. But either way, in this case, it's array of structure, etc., all the way down. And we just have to be kind of consistent with how we're accessing my array, the offset into that array. Inside that array is a structure. I want to access it. That is an array. I need to offset into that array. That is a structure, etc. And so to me, that I guess implies we would go from left to right. But otherwise, we can think of it. We know there's a first name that we want. We can go from inside out or from right to left. But we'll be building structures upon structures because it's just a very natural way to organize the data we have in our program. More of an aside than a critical component, and you may see it just in some code examples you read elsewhere, is this concept of a union type in C. It is a special kind of structure type or struct type in which we may want to have how we are treating individual components in different ways depending on the value of some other component. One way to think about the union structure in C, it is very similar to a regular structure except we're overlapping and we're laying the individual components on top of each other in memory, not side by side in memory. The examples I would come up with today for you would be very synthetic in terms of how we would use it, but it's one way if we want to have some part of some larger struct type where we have some way to determine how to interpret that individual union. So this is similar looking syntax to how we defined our structure. Instead of type def struct and then ultimately the name of the structure, type def union. Otherwise, syntactically, this looks exactly like the definition of a structured type. The union is the union of all the individual components. It's not including all the separate components. So in terms of where this would get laid out in memory, there'd be space for 4 bytes, but at the same location would be a space for that integer, and at that same location would be the space for that float. So does a variable of that type, does it include 4 bytes, or does it include an integer, or does it include a float? Well, that then becomes up to your program in terms of how it wants you to interpret that particular location in memory. Ultimately, whether it's an int or a float, it is ultimately just bytes in memory. So this abstraction is always our correct way of thinking about what's happening in memory. The union type then allows us to kind of decide at a programmer time and ultimately at runtime how we want to interpret those bytes. I can store an integer by doing .integerval. I could then choose to grab the individual bytes of that integer val just by doing .bytes. That would not be 4 separate bytes. Those would be the same 4 bytes that would be storing that integer val. I could then choose if I wanted to now interpret those 4 bytes as a floating point value as well. One way you can use those unions is part of some larger struct in which you would include a variable of that type inside the structure, and then some way to determine how we want to interpret it. So some sort of character or byte to indicate if it's an S treated as a string, or I treated as an int, or F treated as a float. But in terms of the memory usage, a variable of this multi-T type would only be 4 bytes. If it wasn't a union, and if instead it was a struct, it would be 12 bytes, because we would need the storage for the 4 bytes, plus 4 bytes, presumably, plus 4 more bytes. I think sufficient for our understanding of unions is just to be aware that they exist. I think that's sufficient for now. We won't play with them in our lab, so they're like structures, but they allow us to overlay on memory the individual components versus separating out where they are put in memory. But when we start to talk about unions and kind of the flexibility, where sometimes we treat it as a byte array, sometimes we treat it as an integer, sometimes we treat it as a float, as well as structures of arrays of structures and kind of combining and building that hierarchy of these individual structured data types. This use, as well as the associated functions we would be writing for those structures, this use of custom data types and associated functions to handle those variables of those types gets us closer to a kind of a separate programming paradigm referred to or known as object-oriented programming. Has anyone heard the term before? There was a time it was a very popular way to kind of teach introductory programming. Depending on what courses you take, you may still learn some object-oriented programming. The concept of object-oriented programming is we do think about objects first. In our C-based programming, we think about variables and functions primarily. In object-oriented programming, we think about our objects first. The idea, our data and how it's packaged together, that's encapsulation, and then the functions that we define to correspond to be mapped with that data is what defines something as being object-oriented programming. Kind of the original design criteria of C++ was to support object-oriented programming in addition to what C as a programming language already supported. Now, C++ has grown and branched off significantly since then. You can still do the type of code examples I'll show here just very briefly, but you can do also so much more as well. I won't belabor the point about inheritance and polymorphism. You know, if you take advanced programming class, you may get the chance to learn them. But when you start to see C++ code that looks maybe more like this, where in our C here on the side, we have a structure we've defined that has maybe a string, has an integer, and has the name of that structure. And then somewhere else, we have various functions defined that are going to operate on that structure, print person. In an object-oriented language, like kind of vanilla C++, syntactically, we're doing something very similar, except we're directly associating the functions with the type itself. You could still have written print person as a separate function, but instead in C++, what you would do class, which is effectively just still a structure type, name of the structure, name of the object we're creating, the various components associated with the data stored in that structure, as well as now what functions are defined to be directly associated with that structure. So I have a person, and I have a print function associated with that person object, and when I want to print a person, a variable of that type, I don't have to remember the name of a particular function here that takes a person as an input. My variable itself of that person type will have an associated method that I could then call that would give me effectively the same kind of result. That is part of the object-oriented programming paradigm. There's other aspects as well, like inheritance, which we can kind of hack together something with C to give us a concept of inheritance, but it would be a little hackish. In C++, what we could then do is say, this is class person. I'm separately going to create class student that would be inherited from class person, because a student would then be sort of a special type of person. And those variables, those components would already be defined for that class student. I'd have a name, I have an age. I'd also have a print function defined for that student. I could then choose to add what other additional things on top of the base person class I want to have for that student, like GPA or year or something like that. That allows you to really kind of build up more complex objects and more complex functionality by really thinking about the data type and their associated methods first. Oftentimes, if you're doing very pure object-oriented programming, you're designing your classes before you write a single line of code that does anything with those classes, and really focusing on that part. But that would be a separate class, no pun intended. In this class, we stick with C in our structures, and I think we can still see the value of having those structures, even though we don't have methods, but we're kind of defining our own sort of helper functions associated with the structures we've been created. So I'd like us to go through a relatively quick problem-solving exercise where we're going to sort an array of students by their last name. So we'll have the same structure we've already been using. We can use the same kind of bubble sort algorithm we've been using all semester. So our main kind of doubly nested for loop should basically be the same without really much change whatsoever in it. And sorting by name versus sorting by a value of 3, an integer value 3 versus 7, that perhaps is a little bit tricky, but that string comp function we've been using all semester, at least as of recently, to compare two strings, does give us that, what was the fancy term it used in the documentation? Lexicographically comparison between two strings. Basically tells us, given two strings, which one is before the other one in the dictionary. And if they're equal, it returns 0. That's how we've been using that function. So with that string comp function, it's basically like the less than operator or the greater than operator for two strings here. So with the structured data, with the algorithm we already have, and with a special function that kind of gives us that comparison operator, this code should look very similar to our previous version of sorting array values. But now we're doing something much more complicated, right? This is much more akin to having a spreadsheet and deciding to sort by that particular column and return all the results sorted by that particular column. But we have everything we need to be able to do that now. So let's give it a try. This was our structure example from Monday and Wednesday. Let's copy that over into structure sort. Well, it's already copied. Okay, so we already have some starter code here we can start with. We have to kind of populate the data. Again, if we remember, our structure for this student example we've been doing has a first name, a last name, a section, maybe that's A, B, or C, a single character for that, and just a couple scores just to populate it with some data. So quiz scores and some lab scores. We need to populate that with some interesting kind of data. So what I have in this example Replit project is just a text file that includes a set of common first names and a common set of common last names here. And we can just generate some randomized students from this list. This that it looks to be first names, maybe female first names, and then most popular last names here. We can see almost certainly my last name. Yeah, not a chance, not found in there. Anyone have a relatively common last name? Miller. Gotcha. Oh, Matthew Smith's not here today. That's unfortunate. His name would probably be in here. Okay, so we have two files that I have the code already here to kind of open the file. We haven't really talked about that yet. Read all those just names just to populate 2 arrays of last names. This is a little bit, not exactly cheating, but kind of pre-computing that I have a known number of entries in each of those files. And if you want to know how many entries are in a particular file, of course, you can open up the file, you can scroll and trust that your mouse pad is going to hold up and scroll to the end, see that there's 4,946 entries in that file. The other command we've used in other contexts already is word count. Word count -L is basically line count, and I can do that, and it'll tell me how many lines are in that particular file. And so I know that's how many entries are in that file. Take my word for it, that's how many entries are in the other file. And if we so choose, then we can define arrays to kind of store the contents of both those files, right? That's a 2-dimensional array here. This is assuming, this is an assumption, whether it's true or not, I haven't checked, that each name, both first and last name, can fit within 31 bytes. Probably enough bytes to store the most popular first and last names, and we'll just have a bug if that's not enough. And then we have an entry if that's the columns. The rows then corresponds to 4,946 first names and 21,000 some odd last names here. So this code is already provided. These are functions we have not generally used yet, although we've been kind of starting to play around with files. For now, we can kind of assume we have a function that does very similar things to our scanf function, but it's fscanf, so file scanf. Instead of reading in from the input of a user typing, it's reading in from an open file. Otherwise, syntactically, it's doing something very similar here. Read in a string, put it in f names of I, do it 4,946 times. That is a way to just kind of initialize a whole array of first names and last names that we can then allow us to just generate some random students along the way. So we need to generate students. We have the names, potential names of students, and we have the array of students already defined. Starting with 10, if we write our sort code correctly, we can change that to 100 and nothing else in the code should change. But for now, starting with 10 students defined here, that is our student data array called students here. So we need to generate some random students. How do we go about doing that? I had mentioned this already, that sometimes the challenge is you want to have multiple files open kind of side by side here. I think it'll let me do this. I'm going to open up main.c twice, because for me, when I'm working with structured data, you really have to have that structured definition somewhere visible while you do so, unless you have a better memory than I do. I know I have students that are of that student data type. For me, at least, I need to have that handy. Print it out, put it in another window. It's the same file I have open twice here. I think Replit will let me do that, because it's just going to be too easy to kind of forget what is a student, what are the components, and the other stuff. Another way to think about that, although we didn't structure it this way, very common to have the .h file open in one tab and the .c file open up in another tab. So you're not guessing. You know exactly what all your functions in your data type is here. Okay, we need to generate some random students. I guess you could say generate num students, random students, because sum isn't very precise. What do we need to start with here? I'm open to ideas. Absolutely. How high should it go to? So this is going to generate num student, or students of I guess, for each time through the loop. The first name and the last name is probably the hardest part here. So we'll add it. But if I want to do students of I, what are the other components? That we'll do quiz 1 to start with. And I mean, there's some unstated assumptions here. This is a EE 285 style quiz. So let's assume it is a score from 0 to 10 or something like that. Integer score from 0 to 10. How do we generate a random score from 0 to 10? If we do 11, it'll give us a value from 0 to 10. Or we could do, nobody gets a 0. We could do rand mod 10 plus 1, but that's fine. Rand mod 11. Do that for quiz 2 as well. As always, copy paste is always your friend. It doesn't, prevent you from thinking, but it saves the typos you could make along the way. We could do the same for labs. The main difference for labs now, for lab 1 and lab 2, is that as a floating point value. What are our labs worth again? Okay, good to know. Good to know. If we want to do a floating point value, maybe we could do like 501 and then divide that by 10.0. That'll give me a floating point value in the range 0 to 50. It actually doesn't matter. We could also multiply to 51 times 1.0. That should work. Do the same for lab 2. It's not truly random because someone's not going to get a fractional value with this approach, but that's fine. It's a floating point value. How about section number? Assuming it's A through C for the section number. How would we do that?
You could do like mod 4 to get 1, 2, or 3, and then make it a proper character.
And I said A through D. Did I say A through C or A through D? It doesn't matter. Okay, well, either way, we'll do it. And if you don't want to remember what the ASCII entry is, you can always just put it in there. The compiler will interpret that as the appropriate integer in the ASCII table for A. So if rand returns 0, or rand mod 4 returns 0, I get an A. If it returns 1, I get a B. If it returns 2, I get a C. Okay, those were the quote-unquote easy ones here. Let's put them in the order in which they're defined, although it's fine either way. Now we have a random first name and a random last name. How do we copy one string to another? We can do it manually, but if we don't want to do it manually, somebody else. How do we copy one string to another? Okay, that's it. I always talk about how, is it destination versus source? Well, fortunately here, Replit seems to be helping me out. Syntax looks kind of ugly still, but destination comes first, then source is second. It may be complaining because I have string.h defined. It's complaining because I haven't finished it yet. Destination first, and then the source. It's annoying if you get it backwards. Your code's not going to be doing what you think it's going to be doing, but it's destination first here. Our destination, students of I dot first name, the entire name of the array, not like first name of 0 or first name of I or something like that. We're overwriting the entire first name array with a random first name. How do we get a random first name out? We have all the first names stored in F names. So if I wanted the very first name, I would do F names of 0. If I want a random one, how do I get a random one? We know the answer is rand, but not just rand. Rand mod what? Sure. It wouldn't be num student. You could. It wouldn't be wrong. Num students is 10. But we have this array. It has how many first names in that F names array? 4,946. So if we want a randomized index into that array, we can just do mod 4,946. Or, assuming it may change later, mod f num f names. We have this array of size n. If we do rand mod n, we get a value between 0 to n minus 1. That's guaranteed to be an index into that array. So that's going to be a very common kind of code pattern that we would see. Not necessarily randomization, but that mod operator. No matter how big this returns, the end result is a value between 0 and 4,945. That's going to be a valid index into first names. We would then just do the same thing for the last names. Again, got to be careful. Copy paste still saves us time, but now it's last name, and it's not F names, it's L names, and it's not num F names, it's num L names. So again, you copy paste, but then you look at very carefully what you pasted and kind of look at it byte by byte to make sure you've actually changed what you needed here. We have generated num students, random students, because generated random first name, last name, and then just some random scores. We then probably need some way to print this out, and because this is sorting, we're probably going to want to do it more than once here. So let's define functions that'll print out our students. What do you want to call a function that prints out students? Thank you. These are not meant to be hard questions in that sense. What would it take as inputs? It's not void. Could be. We want to print students. And that could be more than the name. It could be the name plus their quiz 2 score. We want the entire student, potentially, right? Print students, plural, versus print student. These could both be valid functions, would do something slightly different, right? Print student, singular, would take a single student. Presumably then, students, print students, plural. I mean, maybe we should name this a little better. I don't know, right? Because it's correct. It's just, you're really making sure your pluralization is correct here. And then usually, except for that C strings where we know how long each array is going to be, when we pass an array to function, unless it's just defined somewhere and we know there's never an issue, it's good practice, to pass in that length information. I'm passing an array of students, and I'm telling you how many there are. And that's what I want you to print out. Let's print an individual student first. I copied the prototype just to put it somewhere else. We could have put it in a C file. You remove this semicolon, you can return. Doesn't do anything other than print. And we can print all sorts of stuff for a student, right? We can print the first name, we can print the last name. Let's do it. Their name is %S. And that would be the student dot first name. Again, once we have that component as a variable, using that component selection or that dot operator, we can do whatever we want with whatever that equivalent data type is. Those are strings. We print them out with %S. There isn't a special print for structures. We're basically writing our own here. Printf, this section. We can also print out some of their scores. I mean, the scores are kind of arbitrary here. There's 2 integers and 2 floats. Seems unhappy, but I think it should be fine. Quiz 1, quiz 2, lab 1. That has printed out an individual student. Now we have print students. See if we can keep all this on the same page here. And we're getting pretty close to being able to call it, right? We're going to do something like, before sorting, students are, or something like that. Student list, that doesn't really matter. We would call print students with our students, and num students here, or it's a little unfortunate. Num students, the variable as an input to a function would be num students, that pound defined value of 10. We could then call this with fewer than 10 students if we wanted to. For our purposes, we're probably printing out all of them. And then we haven't sorted them yet, but this is how we do our sorting, right? We print out the array, we do a sort eventually here. We can guess what that's going to be called pretty soon. Then we print it out afterwards. Print students takes in that array of students as well as a number of students. We know how many there are, right? I mean, it's as many as we provided. So we're back to our for loop. And now we're seeing a little bit of that encapsulation of functions, kind of closer to our lab 6 version of that. If I have a function called print student singular, and I now have an array of students, one way to then print all of the students is just to basically call that function over again. Maybe we want to add like a little header like, this is student D, for student I. And then we would just print student. What would we pass as input to print student? We take as an array, it's going to be passed. It's called students. It's called students in the same place. We could have called it like something totally different, like my students, just to make it difficult. We can. According to this function, that variable is called my students. We're just going to print out student 0, student 1, student 2, student 3. It would be my students of I, yep. And then maybe add a new going to print them out twice. And as with always with random, okay, well, let's add, I guess we should add an extra new line here because it doesn't look good. Before sorting and after sorting should be the same, at least. That's something we can check. And they're randomly generated, so it's kind of hard to say correct or not, but at least it's something, right? So there's student 1, there's good old Gerald Moscow in section B with the corresponding scores that Gerald has gotten in the course. So we have our array. We wrote that print kind of helper function so that we can confirm that the sorting is actually correct. So remember our task here, because sometimes it's easy to forget, sort the students by last name. Before we jump into the sorting, questions about what we've been writing here. So if the question is, did we need to have both a print students and print student? No, definitely not. You could have just written print students and done all that stuff of the name section scores inside the for loop. That would have been fine too. This kind of encapsulates it. Print an individual student, add a little bit of extra data, call print student. You didn't need to do it that way. It could have all just been one function. And as always, it didn't need to be a function. All of this functionality could have just been a for loop on line 57 or 58 or what have you. But since we're doing it twice, right, before sorting and after sorting, when you're reusing that functionality, it might make sense to have it as a function. Any bugs you face, you only have to fix once, and then it should work for those purposes. Questions about this example before we start to sort by last name? We need another function. What do you want to call it? New suggestion, someone who hasn't spoken up yet today. We need a function to sort students. I like it. What kind of input should it have? Possibly. Sort students is sorting all the students, or all the students we pass to it. So usually, at least the way we've been doing our sorting since we learned about arrays, it would make sense to pass that array of students to that function. So when I think about what we need for sort students, it's actually going to be very similar to what we already have for print students. Because it's a function that processes an entire array of students. Take that array of students, print it. Now, take that array of students, sort it. The name maybe isn't that good, right? Because sort students just implies sorting. It doesn't say like sort by last name or something like that. You can write your own functions if you'd like to later, that's fine. But sort students that at least takes in an array of students allows us to then determine what component of the individual student data type we want to do our sorting by. We could sort them by section. We could sort them by quiz 2 score if we wanted to. The main bubble sort code that we've written a couple times isn't really going to change at all. The only thing that's going to change is the less than or greater than operator for that individual comparison that tells us, should we swap 2 students or not? And the rest of the code shouldn't change at all. So we could implement a lot of sorts. For now, I think we just need to implement the one that was specified, which is just sort by last name. But if we want to, we can sort by lab 1 score first, because that's just an extra thing to kind of worry about later. Our bubble sort, we may not remember. It was this doubly nested for loop, of which there was a couple possible optimizations here. One optimization would be, so we have the outer loop, and then there's going to be the inner loop. And the inner loop, we could do it num students, but we actually don't need to, because each time we do that outer loop, we wind up sorting one student in the final, in the closest to Z location, the highest or whatever our sorting criteria is, ordered location. And likewise, we don't need to go to the last element, because when you sort the second to last element and everything up to that, you're guaranteed to have the last element sorted. But we've seen versions of this code that don't have that, and it also worked. It just did some more unnecessary comparisons. So if, at least for our quote-unquote doubly nested for loop implementation of a basic sort, usually looks something like this. I'm going to leave this part as a comment. If reason to swap is true, which, we probably should add some comments to the code in general saying how we're doing the sorting. But if reason to swap is true, we're going to put the rest in the brackets that we're going to add here. First name's less than last name. Quiz 1 greater than quiz 2. We'll implement that reason after the fact. The main mechanism by which we did this sorting is that swapping mechanism. Can we think back? When we had just integers, how did we do that swapping mechanism? We created a temporary variable. It was the one time I feel like calling a variable temp is an acceptable, name for a variable. This is kind of the beauty, I think, of having structured data. I don't really have to think in terms of dot first names and dot last names and dot quiz scores and things like that. Once I've defined that structure, treat it like anything else. Student data temp. Okay? Now I have student data temp, and I'm going to do the swapping. And in fact, at the time I declare it, I can do it. I want to store one of the two values. It doesn't matter how we do it as long as we do it consistently here. Give me the .j value or the j offset. Overwrite the j offset with the j plus 1 offset. And then update the j plus 1 offset with the one we stored as temp. That code, if you were to go back to prior sorting examples, is exactly the same, with the only difference is maybe we didn't call it students, we called it myvals or something like that, and it wasn't student data, it was int. But these structures, although they do seem like complicated, extra kind of things here, even having an array of them, the code is going to be exactly the same with how you work on them. And it's quite nice. We've taken a whole student and swapped it with a whole other student, and all the underlying components of those students do wind up getting swapped. I left a comment, not to complicate things too much, when I talked about that, of shallow versus deep copy. These are so-called shallow copied. It copies these whole blocks over. If inside that you have a pointer to something else, you would have to be responsible for doing that copy. But still, with the version that we have defined here where everything is statically allocated, this direct set of operations where we declare a temp and we just swap two values adjacent to each other in an array works exactly the same as when they were just integers or floats or anything else. Then the question now becomes, we do have to implement if reason to swap is true. And if we go back to our spec here, which was last names, sort by last name, string comp, and the nice thing about it is if we get it wrong, we just switch the order around. String comp returns that basically dictionary relative order. Usually we don't look at the actual value it returns. We check if the value is positive, negative, or 0. 0 means the two strings are byte by byte the same, and I forget which one's positive and I forget which one's negative. But we can check both, and if we got it wrong, we just change the sign of what we're looking for. So string comp, again, in the past we were doing string comp of two strings and checking if it was equal to 0, right? That was for monkeys typing, checking if two strings were equal. Other times we've seen that where people do it like that, which is the same, just check if it's equal to 0. In this case, we're checking two strings, and I believe we're checking to see if it's greater than 0. But what are the two strings we're checking? String comp takes two inputs. What would they be? This is the last bytes of code for this example. It is, and yet it's not quite. That is a start. Now you'll do notice compiler is smart enough to tell us something's wrong. String comp takes as input what? This is a good point, so thank you. String comp takes as input what? Two what? Two values of what type? String comp. Anybody? Two strings, or two arrays of characters. That's what string comp takes as input. Why is it unhappy right now? What did we pass it? We passed it two scalar values. What type are they? We pass them to students, right? Two struct students. It's not what it's looking for. What do we actually want to compare it against? The last name of those two students. So it's dot last name for both of them. Took a little while, didn't it? Okay, should be the same kind of randomized names here. I don't really love this new interface. With Maurice Gordon and Jerry Lee Moscow and Nicola Harley, and etc. It'd be great if one of you got randomly generated through this. And then after sorting, that didn't work at all. Oh, there's a bug. There's a good bug in this program. I broke one of my own rules. Doesn't look very sorted at all. All right, take 30 seconds. Don't shout it out. There's a bug that's visible on this page, like on this screen. Of course, it was intentionally created by me to stretch your critical thinking and debugging skills. I want you to get to the point where these are 10-second bugs and not 25-minute bugs. It'll just take time. This is a good 10-second bug eventually. You got it. Okay, good. Others. One of my rule of thumbs I've been trying to follow, and obviously I'm not doing it consistently, is that I kind of like when I've decided on a new function, I kind of want to do three things even before I've written any code in the function, right? I want to have the prototype defined first. I think that's still very good practice. I copy paste that. That becomes the actual implementation for the function, even if it's blank, because I haven't written it yet. What's the third thing you need to remember to do? There's a third thing. It's the third part of a function. Prototype, implementation, and you gotta actually call the function. So we have this nice function. We didn't call it. Laugh at me all you want. It's a pretty common kind of bug though, right? Because you put all that effort, you're really happy that you have it working, and you're staring, and it's just not doing what you think it should be doing, and that's a very common thing. And even with staring at us in the face, we didn't all necessarily get it here. We look at our students, Jacques Max, and then once they're sorted, we get it in last name, appears to be correct alphabetical order. And then again, when we write it using arrays and using these structures, we can go from 10 students to 100 students, and assuming there's enough memory for all that, it's nothing, right? We've just changed that one character, and we've now sorted an arbitrary number of students that we want to have here. And that sort code, one takeaway, is effectively the same. It doesn't look like it at first blush because that string comp looks complicated, but if I had said sort by quiz 1 score, it would have looked really similar to our old sorting code because we were sorting by an integer value. Questions about this example and sorting all of you in class? Okay, a little early, but let's leave things here for today. Before we jump into pointers next week, I think we'll do another structure example on Monday. So come on back on Monday. Otherwise, enjoy your weekend.